Okay. All right. So we were talking about integration of forms over chains in manifolds, right? Over singular chains. And we talked about given a homotopy. So say a one parameter smooth family of maps HT from a manifold M to a manifold N with H0 equal to a map F and H1 equal to a map G. Then you got an associated prism operator P from K chains on M to K plus 1 chains on N. So if you looked at given a singular K cube C, you got a singular K plus 1 cube PC in N, right? Which if you look at this K plus 1 cube, then the boundary of this cube consists of the top side, which is G composed with C, the bottom side, which is F composed with C, and the vertical sides, which are the prism operator P applied to the boundary of C. Okay. So we have this formula. The boundary of PC is G composed with C minus F composed with C minus P of del C, where C is a K chain on a K cube in M or a K chain in M. So if I take omega a K form on N, then the boundary of PC is a K chain in N. Okay, so I can integrate omega over this. So the integral of omega over boundary PC will become the integral of omega over G composed C minus the integral of omega over F composed C minus the integral of omega over P of del C. Now, I can, to this first term, I can use Stokes' theorem for chains. And then this becomes the integral of d omega over PC. And the integral over a form of a form over PC is the same as the integral of P star of that form over the chain C. So the left-hand side becomes the integral of P star d omega over C. Right? We defined this form P star of, we defined for any form alpha, P star of alpha, right? Okay. So, so the left-hand side becomes the integral of P star d omega over C. And the right-hand side, this integral of omega over G composed C, right? This is the same as the integral of G star omega over C, right? Yes, okay. Because this is the integral of over the unit cube in RK of the pullback of omega by G composed C, and that is the same as the pullback by C of G star omega, right? Okay. So this becomes the integral of G star omega over C minus F star omega over C. And this integral of omega over P of del C, again, this becomes the integral of first P star omega over del C, and then again by Stokes, the integral of dP star omega over C.
I'll just use this thing.
Sorry? Any question? Is that okay? Yeah? Okay. And so since this is true for all chain C, all K chain C, we know that if two forms have the same integrals over all K chains, then they are equal. So that implies that P star d omega is equal to G star omega minus F star omega minus dP star omega. So we can write that in this form. G star omega minus F star omega equal to dP star omega plus P star d omega, right? And so this leads us to two applications. So of this formula, so let me call this formula star. So there are two applications. So the first one was Cartan's formula that we saw last time. That if I take my homotopy to come from a vector field, the flow of a vector field, say X is a vector field on M with phi t is its flow. And my homotopy HT is equal to phi t epsilon, okay, for t between 0 and 1. Okay, so then that means that H0 is identity, so that is my F, and H1 is phi epsilon, so that is my G. Okay. Then if I apply the formula star, what do I get? I get that phi epsilon star omega minus omega equal to d p epsilon star omega plus p epsilon star d omega. Okay. So p epsilon is the corresponding prism operator for this homotopy HT. Okay. So then I divide both sides by epsilon. Okay. And then I use the fact that p epsilon star into 1 over epsilon of any form alpha, this converges to the interior contraction Ix alpha, right? Okay. So if I apply that on the right-hand side, then the right-hand side converges to d of Ix omega plus Ix of d omega. And the left-hand side, by definition, this converges to the Lie derivative Lx omega. Is that clear? So this gives us Cartan's formula. All right. Yes? Is this clear? Okay.
Yeah, it's clear.
And another application is to de Rham cohomology. So in a sense, what one could call homotopy invariance of de Rham cohomology. So let me explain a bit what I mean here. So, okay, well, no, actually, before I do this, let me talk about, well, no, I could talk about this, so fine. Actually, yeah, so, okay, let me talk about Poincare lemma, actually. Let me just talk about Poincare lemma as a first step. So Poincare lemma will say the following. So we say that omega, a K form, is closed if d omega is 0. And exact if omega is d alpha for some k minus 1 form alpha. And since d of d alpha, this we've already seen is 0, exact implies closed. Okay. Right. Now, one can ask, is the converse true? Does closed imply exact? So it turns out the converse is true locally. And that is the content of the Poincare lemma. And so locally, in fact, it is true on any contractible open set, say U in M. So how do we see this? So the claim is that if U is contractible, so that means there's a homotopy HT from U to U such that H0 is constant and H1 is identity of U. Okay, so that's what it means to be contractible. There's a small fact which I'm omitting here, that if you are contractible, that means there's a continuous homotopy to a constant from the identity. Then in fact, there is a smooth homotopy. Okay, so that's a small fact which is true. So we can assume this homotopy is smooth. Then we can apply our formula star from here to this homotopy. So then what do we get? We get that for all omega K form on U, okay, we get that, so my constant is my F and my G is identity. So G star omega is just omega. Okay. And since F is a constant, that means that F star omega is going to be 0, right? Because remember, F star omega acting on tangent vectors V1 to Vk is given by omega acting on df of V1 up to df of Vk. So if F is constant, then the derivative df is 0. So F star omega will be 0, right? So this becomes, the left-hand side of our equation star becomes omega minus 0 equal to dp star omega plus p star d omega. And if omega is closed, then the second term d omega is 0. So then the second term vanishes. This becomes dp star omega. If omega is closed. And this means that omega is exact. So omega becomes equal to d of p star omega. All right. So omega equal to dp star omega is exact on U if it is closed. Okay, so this is the Poincare lemma, that on a contractible open set, any closed form is exact. Okay, is this clear? right? Yes, is this clear?
Yeah, it is clear. Yeah.
Okay. Fine. So what does that mean? That means that omega is closed that will imply that on any ball which is contractible, right, omega will be exact on any ball. So therefore, omega will be locally exact, right? Omega is locally exact. Whereas, conversely, if omega is locally exact, so in the neighborhood of a point, if omega is equal to d alpha, then the operator d is local. It's given by taking derivative. So then d omega will be 0, right? If omega is locally d alpha, then d omega will be 0. So if omega is locally exact, then it will also be closed. So that means that omega is closed if and only if omega is locally exact. Okay. Is this clear? Yeah. All right. Is this clear? Yeah.
Yeah, it's clear.
Right. Okay. So, yeah. Okay. So, as a last application, we can talk a bit about de Rham cohomology and its homotopy invariance. So you would have seen in your algebraic topology that homotopic maps induce the same map on homology, right? And well, therefore also on cohomology, right? Yeah, so homotopic on singular homology and singular cohomology, homotopic maps induce the same map, right? So the same is true actually for another cohomology called de Rham cohomology. So de Rham cohomology is defined as follows, that the kth de Rham cohomology group, so this is a real vector space. This is defined to be the space of closed K-forms modulo the space of exact K-forms. Okay. So as we remarked above, the exact K-forms are contained inside the closed K-forms, right? So we can take this quotient. Yeah. And if I have F is a smooth map from M to N, right? Then it induces a map on de Rham cohomology, F upper star, which goes in the opposite direction from the de Rham cohomology of N to the de Rham cohomology of M. So the equivalence class of some closed K form omega goes to the equivalence class of F star omega. Okay. So notice this is well defined because first of all, if omega is closed, then F star omega is also closed by the naturality of pullback, by the naturality of the, of the exterior derivative. So D of F star omega is f star of d omega, which is 0, right? And also f star of, if I take a different representative of the same equivalence class, so that's of the form omega plus some exact form d alpha, this will become f star omega plus f star of d alpha, and that is f star omega plus d of f star alpha. So that means when I pull back, I stay in the same equivalence class, right? Because I'm just changing by an exact form. Okay, so this gives a well-defined map from de Rham cohomology of n to de Rham cohomology of n. Is this clear? Okay. Yes? And what does our formula give us? That if omega is a K form on n, is a de Rham cohomology class. So that means omega is a closed K form on n. And I have two homotopic maps from M to N. So smoothly homotopic, I can assume. Then G star omega minus F star omega, this is dP star omega plus P star of d omega, but that is 0 because P star of d omega is 0 since d omega is 0. So that means that G star omega and F star omega differ by an exact form. It's d of P star omega. This is an exact form. So that means that G star omega, this de Rham cohomology class, is the same as F star omega. Okay. So that means that the induced maps on de Rham cohomology are the same. So G star is equal to F star as a map from de Rham cohomology of n to de Rham cohomology of n. Is this clear? So this is the homotopy invariance of de Rham cohomology. Homotopic maps induce the same map on de Rham cohomology. Is this clear?
Yes, sir, it's clear.
Okay. So these are some applications of the prism operator. So, I mean, it's just the dual theory to what you do for homology. The prism operator in homology is used to prove the homotopy invariance of homology, right? So similarly, you can use it to prove the homotopy invariance of de Rham cohomology. Is this clear? Yeah. Okay.
Yeah, it's clear.
Okay. So you can read more about de Rham cohomology groups in, say, Bottom 2. There are many books you can read. I won't talk more about them. Okay. So I just want to get to the basic definitions we'll be needing. So we now want to talk about integration of n forms over n manifolds. So integration of a top degree form. Okay. So now suppose M is a smooth n manifold of dimension n, and suppose omega is an n form on M. Okay. So suppose C is an n cube in M, a singular n cube. And suppose I take a reparametrization of C. So what I'm going to do is compose C with a diffeomorphism sigma from the n cube to itself. Okay. So sigma you think of as a reparametrization. All right. So it's a smooth diffeomorphism from the n cube to itself. So first of all, we can look at omega tilde, which is the pullback C star of omega. So this is going to be some function h times dx1 wedge dxn. And now I can look at the reparametrization of C. So that is C composed with sigma, the pullback of omega by this map, right? So pullback by C composed sigma star is going to be sigma star composed with C star. So this will become sigma star of omega tilde. And so now omega tilde is this form on the n cube, h dx1 wedge dxn, right? So dx1 wedge dxn on the n cube, at each point, this is just the determinant, right? It's the determinant form with respect to the standard basis. So we know what happens when we pull back the determinant by a linear map. We get the determinant of that linear map into that n form, right? So when I pull back, this is going to become h composed with sigma into determinant of d sigma dx1 wedge dxn, right? Is that clear? Yeah. Recall that for any n form on a n-dimensional vector space, if I pull back by a linear map, T, then T star of omega is determinant T into omega, right? Yeah, we saw this long ago, right? Yes? Right, for an n form omega on an n-dimensional vector space, the space of n forms is one-dimensional, right? So T star omega is some constant times omega, right? Yes, that constant is nothing but the determinant of T. So here at each point, we're pulling back by the derivative d sigma. So what's going to come out is determinant of d sigma. Is that clear? Yes?
Yes, sir.
Yeah, it's clear. Yeah.
Okay, fine. All right. So now let's look at the integral of omega over c. So this by definition is the integral of hx dx1 dxn over the unit cube. Now, here I can make a change of variable x equal to sigma of y, right? And then by the change of variables formula from multivariable calculus, this is going to be the integral over the unit cube, h of sigma y, the modulus of determinant of d sigma at y, dy1 dyn, right? Okay. On the other hand, if I look at the integral of omega over the reparametrized cube, c composed with sigma, then this is the integral over the unit cube of c composed sigma star of omega. So that's going to be the integral of this function, h composed sigma determinant d sigma, so over the unit cube. So this will be the integral of h of sigma y, determinant of d sigma at y, dy1 dyn, right? So what do we see? We see that these two integrals are the same if and only if the determinant of d sigma is positive everywhere, right? So notice one thing, that since sigma is a smooth diffeomorphism, right? The determinant of d sigma, that is non-zero everywhere. So by connectedness, it is either positive everywhere or negative everywhere, right? It doesn't change sign because determinant d sigma is non-zero everywhere, right? So by connectedness, it has to be either positive everywhere or negative everywhere. And so there are two cases. We say that sigma is orientation preserving if determinant d sigma is positive everywhere, then what happens is these two integrals are the same. So the integral of omega over sigma is the same as the integral of omega over C composed sigma over the same cube but reparametrized. All right. Whereas if sigma is orientation reversing, that means determinant d sigma is negative, then the integral of omega over C becomes minus the integral of omega over C composed with C composed with sigma, right? Is this clear? Yes? Okay. So we can see that the integral is not quite invariant under reparametrization. It depends on whether the reparametrization is orientation preserving or orientation reversing, right? Is that clear? Yeah.
Yeah, it's clear.
Right. So see, now one can imagine, suppose we have an n form on an n manifold. I want to define its integral, right? So suppose I have omega is an n form on an n manifold. Okay. So for example, like this, say a 2 form on a 2 manifold, right? Then what I can try and do is divide up my manifold into cubes, right? So for example, I can take the upper hemisphere to be 1 cube and the lower hemisphere to be the image of another cube, say C1 and C2, right? And so instead of a triangulation, you take a cubulation, right? You cubulate your manifold, okay? So divide it into cubes, where, I mean, this C1 and C2 are diffeomorphisms from the interior of the cube to the interior of their image, all right? So then you could try defining the integral of omega over, say, your manifold M. You would like to say this should be the integral of omega over C1 plus the integral of omega over C2, right? This would be a natural definition. Yes? But the only problem is that here we don't have a canonical choice, first of all, of these parametrizations. So we could, a priori, we could reparametrize, right? I could take C1 composed with some sigma 1 and C2 composed with some sigma 2, where sigma 1 and sigma 2 are diffeomorphisms from the cube to itself, from the square to itself in this case. In that case, we don't know, I mean, these integrals might change sign, right? So then we won't have a well-defined integral over n, right? Okay. So somehow we need to choose correct parametrizations of these cubes in M. So that will require the notion of an orientation on M. Okay, so let's stop this session and now we'll talk about what is an orientation on a manifold. Okay, so. Okay. So we see that when trying to define the integral, we have this problem of how to choose the parametrizations of these upper and lower hemispheres, right? That if we reparametrize by orientation reversing diffeomorphisms, then these integrals would change sign, and so the integral over the manifold may not be well defined, right? So how do we get a well-defined integral? For that, we need a notion of what is called an orientation on the manifold. Okay. So what is an orientation on a manifold? Well, recall that we defined an orientation on a finite dimensional vector space. It was an equivalence class of ordered bases, right? Where given two ordered bases, V1 to Vn and W1 to Wn, you look at the unique linear map T, which sends the Vi's to the Wi's. Then you say that the Vi's are equivalent to the Wi's if the determinant of T is positive, right? So this gave an equivalence relation on ordered bases, and orientation was an equivalence class, right? So there were just two equivalence classes on your vector space V, which corresponded to the two connected components of GLV, right? So linear maps with positive determinant and invertible linear maps with negative determinant. These are the two connected components. So geometrically, you can think of two ordered bases giving the same orientation, if and only if you can deform one continuously into the other, right? Okay. Because then they lie in the same connected component. Now, what is an orientation on a manifold? That is the following. So let nu naught be the standard orientation on Rn, given by the ordered basis E1 up to En, the standard basis of Rn. And let nu naught op denote the opposite orientation. Okay. So an orientation on the manifold M is a choice of orientation mu p, where p ranges over M on each tangent space TPM. Okay. So for each tangent space, we're going to choose an orientation mu p on TPM. Okay. And we want this choice of orientations to be continuous in the following sense. Okay. So an orientation is going to be a continuous choice of orientations on each tangent space. So what does it mean for this set of orientations to be continuous? It means the following, that if I take any chart u comma phi, then what I can do is at each point, I have an orientation mu p on my tangent space TPM, and I have the derivative of the chart d phi at p. So this is a linear isomorphism from TPM to Rn, right? So I can look at the push forward of this orientation under d phi p. So what is the push forward of an orientation? That means that if mu, that's the equivalence class of, say, an ordered basis V1 to Vn, if that is an orientation on V, and T from V to W is an invertible linear map between vector spaces VW, then the push forward orientation T star mu is equal to the equivalence class of the ordered basis TV1 to TVN. Okay, so just take any basis in your equivalence class, look at its image under T, that will be an ordered basis in the image vector space, take its equivalence class. Okay, that is the push forward orientation. So it's easy to see this is well defined. This is an orientation. This is independent of the choice of representative of the equivalence class. Okay. So what we want is that for all points in this chart U, for all points P in the chart U, the push forward of mu P by the derivative of phi at P, either this is equal to the standard orientation at all points in the chart, or the push forward is equal to the opposite orientation on Rn at all points in the chart. Okay. So in this sense, the choice of orientation is continuous. Okay. Is the definition clear? Yes. Okay, so an orientation may or may not exist on your manifold. So for example, if we take a surface sigma inside R3, so that's a 2 manifold sitting inside R3. Okay. Then so yeah. So suppose I have an orientation on sigma. So that means on each tangent space, I can choose an ordered basis, which gives me the orientation mu p, right? Then at this point of the surface, I have two normal vectors, right? There are two unit normal vectors, right? So there's a unit normal vector n like this, and there is minus n, right? So now, how do I choose one of these two normal vectors? Well, what I do is we choose the normal vector n such that so given an orientation mu p, so that is the equivalence class of some basis, say v1, v2 on TPM. So TPM, this is now a subspace of R2, sorry, of R3, right? TP sigma, sorry, TP sigma. Okay, you choose the unit normal at P, n of P, okay, such that if I look at, say, n together with this, so if I look at V1, V2 together with n, P, so this will be a basis of R3. I want this to give the standard orientation on R3. So this should be nu naught, okay? So there is a unique choice of unit normal, so that this basis of R3 gives me the standard orientation on R3, right? If I choose minus n, then I'll get the opposite orientation, right? Is it clear? So sigma orientable will imply that sigma admits a continuous unit normal vector field. N, so this will be a map from sigma to R3. Well, it will take values in unit vectors in R3. So this will be a map to S2 in R3. Okay, P goes to NP. Okay, where NP is such that NP is orthogonal to TP sigma and V1, V2, NP is equal to nu naught if mu p is equal to v1, v2. Okay, so NP is uniquely determined by these two conditions, right? It's a unit vector which is orthogonal to the tangent space. And when I add it to a basis which gives the orientation of the tangent space, then I get the standard orientation on R3. Is this clear? Okay. And what one can see is that conversely, if you have a continuous unit normal vector field on sigma, then you get an orientation of sigma by following the same rule that if I take NP, then if I take an ordered basis, say V1, V2 of TP sigma, then I say that my orientation mu p is given by V1, V2 if the ordered basis V1, V2 nu NP is equal to the standard orientation on R3. So actually this is if and only if. Okay, so sigma will be orientable if and only if it admits a continuous unit normal vector field. All right, this is not hard to see. Is this okay? Yeah. So for example, of a non-orientable surface, the standard example is you can take the Mobius strip, right? So okay, so sigma equal to the Mobius strip. This is not orientable. Because if I start with a unit normal vector field here, if I move along a curve, and if this unit normal vector field is continuous, then along the curve it's continuous, but when I come around, then when I make a full circuit, then I end up with the opposite unit normal that I started with, right? When I go once around the Mobius strip. Okay, so you can't have a continuous unit normal on the Mobius strip. Therefore, it is non-orientable. All right. Is this okay? Yes, any questions? Is this all right? Yeah.
Yes, sir, it is all right.
Okay, okay. Thank you. Thank you. Okay. All right. So that's just a little bit about orientation on a manifold, just to give you an idea. So M is orientable if it admits an orientation. Okay. So in this case, there are only two possible orientations on M if M is connected. Okay. So an orientable manifold can have at most two possible orientations. Okay. That is not hard to see. You can show that as an exercise. So now given an orientation on a manifold, okay, so if we're given an orientation mu, which is a collection of orientations mu p on the tangent spaces TPM, then we can define a good class of charts. We say that a chart u comma phi is orientation preserving. So I'll write OP for short. If the derivative of the chart at each point P in the chart pushes forward the given orientation mu P to the standard orientation on Rn. All right. Okay. So notice that if I have any chart, from that I can always get an orientation preserving chart, Because if it is orientation preserving already, then I don't have to do anything. But if it is orientation reversing, that means it pushes forward the given orientation mu p to the opposite of the standard orientation on Rn. Then I can just compose with a reflection in Rn, right? From Rn to Rn. That will push forward back to the standard orientation on Rn. So a reflection composed with my chart will become orientation preserving. Is that clear? So there always exist orientation preserving charts, right? Okay. Is that clear? Yeah. Okay. So now suppose that I have two orientation preserving charts, U phi and say V comma psi. So let sigma, which is psi composed phi inverse, let this be the change of charts, right? So then if I take a point P in the intersection where this sigma is defined, so then, so sigma is defined on the image of this under phi. So what do I have? I have that nu naught, because psi is orientation preserving. This is given by the push forward under d psi of mu p, but psi is equal to sigma composed with phi. So the push forward by d psi by the chain rule is the push forward by d sigma of the push forward by d phi, right? And d phi pushes forward mu p to the standard orientation because phi is also orientation preserving. So this composition, this becomes the push forward of the standard orientation by d sigma at phi p, right? So what does that mean? That means that d sigma at each point phi p, it pushes forward the standard orientation to itself. So if it pushes forward the standard orientation to itself, that just means that the determinant of d sigma is positive, right? Is that clear? Yeah. So the change of charts will be an orientation preserving diffeomorphism from Rn to itself. Is that clear? Yeah. Okay. Yes, is that clear? Yes, are you there? Anyone there?
Yes, sir, it is clear.
Okay, thank you, thank you. Yeah, okay. All right. So now suppose we have an oriented manifold N with orientation mu. So the dimension of M is N. So suppose omega is an N form on M, and let us suppose that the support of omega is contained in U for some orientation preserving chart U phi. Okay. So the support of omega means the closure of the set of points where omega is non-zero. Okay. So omega is zero outside the support of omega. All right. So suppose the support is contained inside some orientation preserving chart U phi. Okay. So then we have a form omega tilde, right, which is an N form on the image of U. So phi of U is an open set in Rn, and omega tilde is an N form on this open set phi U in Rn, such that omega is given by the pullback phi star of omega tilde. Okay. So omega tilde is some N form on an open set in Rn, so it's of the form H dx1 wedge dxn, where H is a smooth function with compact support inside phi of U. Okay. So then we define the integral of omega over M to be the integral of this function H dx1 dxn over the image phi of U. Okay. Which is by definition the integral of this omega tilde over phi of U. Okay. And so what we're doing is defining the integral of a n form on my oriented manifold M, whose support is compact, contained inside an orientation preserving chart U. Okay. So we have this is my chart U, and say this is the support of omega. Omega is supported here. So I have my chart phi, and this goes to some open set phi of U in Rn. Okay. And then I get a form omega tilde, which is supported here inside phi of U, such that omega is equal to phi upper star omega tilde. Omega tilde is equal to some function h dx1 wedge dxn. Okay. And then the integral of omega over n, this is defined to be the integral of this function h over phi of u. Okay. So this integral is well defined because h has compact support. It's continuous with compact support. Okay. All right. Yeah. So what one has to check is that this is independent of the choice of orientation preserving chart phi, right? So this is where our orientation comes in, that if we have another orientation preserving chart, say V psi, such that the support of omega is contained inside V, right? So then the support of omega is contained inside U intersect V. So I have then some V here, right? And I'll get my chart here psi. So this is psi of V. Yeah. So here I'll have another form. Say omega hat. Okay. Right. And here I have a change of charts map, sigma. Okay. So here my omega hat is defined such that omega is equal to psi upper star omega hat. Okay. So I have that omega hat. So omega is equal to, so psi upper star omega hat, and psi is equal to phi composed with sigma. So this is phi, sorry, sigma composed with phi, sorry. Sigma composed with phi. And so this will become phi star of sigma star of omega hat. Okay. And this is also equal to phi star of omega tilde. So that implies that the form here, omega tilde, and the form here, omega hat, they are related by omega tilde is equal to sigma star of omega hat. Okay. And so if omega hat was equal to, say, some function, what do I have here? Probably h. Well, okay, fine. So, yeah, so we want to see that the two integrals are the same. The integral of omega tilde over phi u, we want to see this is the same as the integral of omega hat over psi v. So why is that? First, note that because the support of omega is contained inside u intersect v, that means that the support of omega tilde is contained inside phi of u intersect v. The support of omega hat is contained inside psi of u intersect v. And psi of u intersect v is equal to sigma of phi of u intersect v. So now if we start with the integral of omega tilde over phi u, then because this is supported inside phi of u intersect v, this is the same as the integral of omega tilde over phi of u intersect v. And now I can write on phi of u intersect v, omega tilde I can write as the pullback sigma star of omega hat. So this integral over phi of u intersect v, this is going to be the same as the integral of omega hat over sigma of phi intersect uv, or sigma of phi of u intersect v. In this step, we use the fact that sigma is orientation preserving, that these two integrals are the same. Okay. Right. So sigma is orientation preserving because phi and psi are both orientation preserving charts. So as we just saw before, the change of charts is orientation preserving. That will imply that these two integrals are the same. And then this integral over sigma composed phi of u intersect v is the integral over psi of u intersect v. And that is the same as the integral over psi of v of omega hat. Okay. So these two integrals are the same. Okay. So this integral of a compactly supported form with support contained inside a chart, this is well defined. All right. Is this clear?
Yes, sir.
Yeah. Okay. So to go from here to here, we need to use the fact that sigma is orientation preserving. If it was orientation reversing, then these two would be negatives of each other. That's all. Okay. So this is well defined because we are using orientation preserving charts. And we have the class of orientation preserving charts because we have an orientation on M. Right. All right. So now we also define the integral of mod omega over M to be the integral of the function mod h dx1 dxn over phi of u. Okay. So now we can define the integral of a general form over my manifold using a partition of unity. So let ui psi I be orientation preserving charts where ui is a locally finite open cover of M. So locally finite means that any compact set in M intersects only finitely many of the ui's. Okay. So now, since this is a locally finite open cover, we can choose a partition of unity phi I, which is subordinate to this cover ui. Okay. So that means that each phi I has support. It's a continuous function, a smooth function with compact support, with the support contained inside ui. Okay. And the sum of the phi i's are all greater than or equal to 0, and the sum of the phi i's is 1. Okay, at each point in the manifold. So given this partition of unity, and given an omega which is an n form on M, we say that omega is integrable if the sum over I of the integral of over M of mod phi I omega, this is finite. Okay. So notice that phi I omega, this will have support contained inside ui. Okay, which is an orientation preserving chart. So this integral of mod phi omega over M, this is well defined, right? Okay, so we'll say that omega is integrable if the sum over I of these integrals mod phi omega is finite. Okay, and if omega is integrable, then we can take the sum over I integral of phi I omega over M. Okay, this sum will converge because the above sum is finite. Okay. So in particular, if N is a compact manifold, then any N form will be integrable because this sum will just be a finite sum. You can always take a finite cover. Okay. Is that clear? Yeah. Okay, so the fact is that this definition of integrable form, this is independent of the choice of partition of unity. Okay. So, and this integral of omega using this partition of unity, this is again independent of the choice of partition of unity. Yeah. Fine. So that defines the integral of an M form over an N manifold. All right. So the last thing we need to define is manifolds with boundary and the integral over the boundary of a manifold with boundary, right? Yeah. So let me define for you what is a manifold with boundary. So for a manifold, the neighborhood of any point is homeomorphic to an open set in Rn or a ball in Rn, right? So for a manifold with boundary, we will just have that. So for example, if you take, say, this manifold with boundary, you take a torus and you cut out a disk, right? Then this becomes a manifold with boundary. That means at these points, you have a neighborhood which is homeomorphic to a neighborhood of a point in the boundary of a half space. Okay, so this is, say, the upper half space in R2, and a neighborhood here is homeomorphic to a neighborhood of a point in the upper half space, a neighborhood of a point on the boundary of the upper half space. Okay, take a neighborhood in the upper half space. So this is the local model for boundary points. So in general, in higher dimensions, you define the upper half space, the closed upper half space, to be the set of x1 to xn in Rn, where xn is greater than or equal to 0. Okay. So this is Hn, the closed upper half space. And then you need to define what is a smooth map from an open subset of the half space Hn into Rm. So here I could take a subset of the half space which looks like this. Okay. And I could take a map which goes into Rn, some Rn. So you say this is smooth if at each point it extends to a neighborhood in Rn. Okay, it has a smooth extension to a neighborhood in Rn. So, okay, let me stop this session and start a new session. So, all right, so we're going to define what is a manifold with boundary. So we have to define what is a smooth map on an open subset of the closed upper half space Hn. So we say that F from an open subset U and Hn to Rm is smooth if for any point P in U, there exists a open neighborhood of P in Rn, okay, V, and there exists a map F tilde on V. So V is an open subset of Rn taking values in, and F tilde takes values in Rm. So this F tilde is smooth, and F tilde restricted to V intersection U is F. Okay. So that's what we're seeing in this picture here. So at a point P in U, we have a neighborhood in Rn. Okay, this V here, and we have a smooth map F tilde on V, which agrees with F on V intersect U. Okay, so locally F extends to a smooth map in a neighborhood in Rn at each point of U. Is this clear? Yeah. Okay, we need to make this definition because a priori smooth functions are defined on open subsets of Rn, right? We don't have a definition for a smooth function on a closed set in general, or an arbitrary set. So the definition that we're taking is that at each point you have a neighborhood in Rn where you have an extension of F to a smooth function on that neighborhood in Rn. Okay. Is this clear? Yes? Okay. So then, if I take a point P in the boundary of the closed upper half space, then if I take any derivative of F tilde at P, right? Since F tilde is smooth, I can write this as a limit of that derivative of F tilde approached from points Q in the interior of the upper half space, right? Because F tilde is smooth, but in the interior of the upper half space, F tilde is equal to F, right? And so this becomes a limit of the derivatives of F, okay, approached from points in the upper half space. So this limit exists, okay, for any point on the boundary of the upper half space, right? And so we can define any partial derivative of F at any point on the boundary of the upper half space to be the corresponding partial derivative of the extension F tilde, right? This is independent of the choice of F tilde because it is just a limit of the partial derivative of F approached from points in the upper half space, in the interior of the upper half space. Okay. All right. So now we can define what is a manifold with boundary. So it's a second countable Hausdorff space like a manifold. So together with the family of charts ui phi I, so the ui's are an open cover, where for all I, phi I goes from the open set ui to some set vi in Rn, and phi I is a homeomorphism where vi is either an open set in Rn or it is an open set in Hn in the closed half space. Okay. So that's the only difference as so far with the definition of smooth manifold, that your image in Rn is either open in Rn or it is open in Hn. Okay. And the third condition is that whenever you have two charts ui, uj which intersect, then if I look at the change of charts map, so this is defined from phi I of ui intersection uj, that is an open subset of vi, and that this maps into Rn. This map should be smooth, where the only difference with the previous definition of manifold is that this vi now may be an open subset of Hn. It need not be an open subset of Rn. Okay. So if vi is an open subset of Hn, then this phi j composed phi I inverse is defined on an open subset of Hn, right? And this is smooth as defined above. Okay. All right. So then we say that P, a point in M, is a boundary point of M if phi of P belongs to the boundary of Hn for some chart phi near P. Okay. So it turns out that actually this is independent of the choice of chart, that if P maps to the boundary of Hn for some chart phi, then it maps to the boundary of Hn for all charts psi. So how do you see that? So here you have your manifold. So say it looks like this. So say you have two charts which contain P. This is a U and this is a V. And this is my P. So suppose this maps to the boundary of Hn here. Okay. This is phi of P is in the boundary of Hn. And suppose I have a psi. Right. So if psi does not map into the boundary of Hn, right? So then it maps into some ball in Rn. Okay. Right. And then I can look at the change of charts map going this way. Right. So this is going to be phi composed. So say sigma. This is phi composed with psi inverse. Okay. Now sigma is going from a neighborhood, say this is some ball B in Rn. Okay. So sigma is going from an open subset of Rn into Rn. Okay. Now this is a continuous one-to-one map from Rn to itself. Okay. Therefore, by a theorem called Brouwer's invariance of domain, sigma is an open map. But then that means that sigma of this ball B so that means that sigma of B, this contains a ball around this point in the image, phi of P. Okay. But then you get a ball in the image around phi of P. But that ball also contains points in the lower half space. But that's a contradiction, right? Because sigma is, the image of sigma is contained in the image of phi, right? And phi takes values in the upper half space. Okay. Right. So sigma of B would intersect the complement of the upper half space. That's a contradiction. Okay. Since image of phi is contained inside the closed upper half space. Is this clear? Yeah. So you cannot have P mapping into an interior point of Hn if it maps into the boundary of Hn in some chart. All right. Is that clear?
Yes, sir, it is clear.
Okay. So that means that boundary points are well defined. Okay. So once boundary points are well defined, what does that mean? That means that if I take this chart phi, then so all of the so that means that if I look at phi of U intersect boundary M, right? This is going to be phi of U intersect boundary Hn, right? Yeah. All of the points in boundary M have to map to boundary Hn, right? And conversely, the points in the image of phi which are in boundary Hn, they come from boundary points of M, right? Okay. And what is boundary Hn? Boundary Hn is Rn minus 1 cross 0, right? So this is identified with Rn minus 1. Okay. So this phi of U intersect boundary Hn, this is an open subset of boundary Hn, right? Okay. And this is identified with Rn minus 1. So that means that phi restricted to boundary M gives you a homeomorphism with an open set in Rn minus 1, right? So that means that if I look at my charts, so if I restrict my charts say, to boundary M. So if I look at UI intersect boundary M together with phi I restricted to UI intersect boundary M, right? Then that means that these give me charts on boundary M, right? Such that boundary M is now an n-1 manifold. Is that clear? Yeah. Okay. Is that all right? Yeah. Okay, so restricting the charts on M, restricting them to boundary M gives me charts on boundary M. Okay, so boundary M becomes an n-1 manifold. Is this clear? Yeah. Yes.
Yes, sir, it is clear.
Okay, thank you. Okay, so we've now got the structure of an n-1 manifold on boundary M. So the last thing which I'll just define briefly, I don't want to spend too much time on this, is you have to define an orientation on boundary M. Okay. So this is called the induced orientation on boundary M. So suppose now that M is oriented, then the orientation on M will give an orientation on boundary M. So suppose mu P and M is an orientation on M. Okay. Yeah. So first of all, the tangent space to boundary M, okay, this is naturally identified with, so we have this inclusion map, I from boundary M into M. So this induces one-to-one linear maps the derivative of I at P from the tangent space to boundary M into the tangent space to M. Okay. So we can view TP boundary M as a subspace of TPM. Okay. All right. So if, for example, phi is equal to, say, x1 to xn, right? Is a chart taking values in, say, Hn. Okay. Phi of P belongs to boundary Hn. Okay. So then the tangent space to the boundary will be what? Basically, this chart is mapping. So this is part of M. This is my point P. This is mapping to a point on the boundary of the upper half space, right? So, so phi restricted to U intersect boundary M. On U intersect boundary M, that means we take values in the boundary of the upper half space. That means the nth coordinate xn is 0, right? So this is equal to x1 to xn minus 1, comma 0 restricted to U intersect boundary M, right? Okay. So x1 to xn, these are coordinates, x1 to xn minus 1, these are coordinates on boundary M, right? x1 to xn minus 1, these are coordinates on boundary M near P. Okay. And what happens is that the tangent space to boundary M, you can see this as therefore the span of del del x1 at P up to del del xn minus 1 at P, which is sitting inside the span of del del x1 at P up to del del x n at P, which is all of TPN. Okay. All right. So that's what this subspace is, sitting inside TPM. All right. Yeah. So now if I have a tangent vector at P, then we say that V in TPM minus, so this is my V. I say that this is an outward pointing vector if its image under the derivative of the chart d phi p points out of the upper half space. So V is a tangent vector in TPM minus TP del M. Okay, so say that this is outward pointing. If d phi at P of V is equal to a vector which points outwards, that means it's H1 up to Hn, where the last coordinate Hn is negative. Okay. Is this clear? So this is an outward pointing vector. Again, you can check this is well defined independent of the choice of chart phi. Okay. And then we can define the induced orientation as follows. So if so we define orientation mu p tilde So we have to define an orientation on the tangent space to the boundary, right? Okay, we have to define an orientation on the tangent space to the boundary. So we define it as follows, that mu p tilde is equal to the equivalence class of an ordered basis v1 to vn minus 1 of Tp del m if mu p, that is the orientation on TPM, is given by some outward pointing vector n together with v1 to vn minus 1. Where n, this belongs to TPM minus Tp del m is outward pointing. Okay. Is this clear? Okay, so just let me give you an example. So you see how this works. So suppose M is equal to an annulus, say R less than or equal to mod Z less than or equal to capital R. Okay, inside C, which is R2. Then how does this induced orientation work? So boundary M has two components, right? The outer circle and the inner circle, right? So boundary M is a one manifold. So orientation means ordered basis means just one vector. I have to give a vector and either pointing one way on the boundary or the other way. So what happens on each boundary component? So my orientation on M is, let's say, the standard orientation coming from R2 at each point, okay? And so at a point on the boundary, here, what is my outward pointing vector? It looks like this, right? So I want n comma tangent vector to the boundary. That should give me the standard orientation on R2. So that means over here, I should take this vector, right? V1. So this will give my orientation on the boundary, on this boundary component. So on this boundary component, I will be going anti-clockwise, right? Okay. All right. Whereas if I look on this boundary component, here an outward pointing vector looks like this, right? So if I want the standard orientation on R2, then my second vector should look like this, right? My V1 should look like this. If this is n, this will give me the standard orientation on R2, right? This n comma V1 in this case. Is this clear? So then my orientation on this boundary component will be going clockwise. All right. Is it clear? Yes.
Yes, sir, it is clear.
Yeah. So this is the induced orientation on the boundary. Okay. So to wrap up this preliminary section on integration, now I can state, since we've defined the orientation on the boundary, okay, so the boundary becomes an oriented manifold also. And so then we have Stokes' theorem. for compact manifolds with boundary. So suppose M is a compact N manifold with boundary. So compact oriented N manifold. So I have to assume it's oriented, yeah. So in order to define integration. So N is a compact oriented N manifold with boundary. So then del M is also an oriented N-1 manifold. Then for any N-1 form, omega, the integral of d omega, so that's an N form, I can integrate it over N, right? This is equal to the integral over boundary M of omega. Okay. Yeah, so boundary M will become is an N-1 manifold. I can integrate, it's an oriented N-1 manifold. I can integrate my N-1 form over it. Okay. Is this clear? All right. So this is Stokes' theorem. So I just remark that the right-hand side is equal to 0 if it's a manifold without boundary. So if boundary M is empty. Okay. In that case, the integral of d omega over M is equal to 0. So the integral of an exact form over a manifold without boundary is 0. Okay. Is the statement clear?
Yeah, it's clear. Yeah.
Yeah. Okay, so any questions about integration, Stokes' theorem? Any questions? We have a few minutes left, so we can discuss anything you want to discuss. I won't start anything new. There's just about 4 minutes left. So it's no point starting a new topic now. But if there's anything about integration, any questions you have, we can talk about them. Any questions? So from next time, we'll start talking about vector bundles and connections on vector bundles. Because that will be essential when we talk about harmonic maps and their derivatives and higher derivatives and so on. So
Sir, so
yeah.
that for this Stokes theorem, the integral over M would be 0 if it's a manifold without boundary.
Right. The integral is 0 if it's a manifold without boundary. Right. Yeah. The integral of any exact form is 0 if it's a manifold without boundary. Yeah.
Oh, yes, sir.
Right. Hmm. So what that means is if you have a manifold without boundary, then suppose M is compact without boundary and oriented. Okay. Suppose it's an oriented compact manifold without boundary. So for example, a surface of genus G, right? This is orientable and without boundary. So then you have what's called the integration pairing. So this is a bilinear pairing between your kth homology with real coefficients and the de Rham cohomology, kth de Rham cohomology. This is the integration pairing. So here you take a homology class, say C, and you take a cohomology class, de Rham cohomology class. And so this homology class you can represent by a singular chain, and then you C and you integrate omega over C. Okay. So this is well defined because if I change, oh, sorry, what am I? Oh, no, this doesn't need, okay, fine. No, okay. For Stokes' theorem, yeah, no, that would give you the well-definedness if you look at the top homology. Okay. Right. So, no, I'm being silly. Yeah, for this, this well-defined just needs Stokes' theorem for chains. So, yeah. Sorry. I didn't, yeah, sorry. Yeah. No,
This pairing is actually non-singular, right? Singular.
That's right. That's right. This is non-degenerate. Yeah. So this pairing is non-degenerate. Yeah. So, yeah. Correct. This pairing is non-degenerate. If you have any more questions, I can just continue for a little bit. Otherwise, I can stop. So. Okay, then let me